Bridgeport RESCO, a Wheelabrator waste management company, is pleased to provide as an educational service this issue of Science Screen Report.
Energy. Our ability to control it makes civilization possible. Without using energy, we couldn't light our cities, travel at high speeds, or delve into the secrets of nature. We depend on our energy resources to keep civilization functioning. That's why, as fossil fuel supplies are used up, renewable energy that draws power from the sun, water, and even from deep within the earth itself becomes vitally important. Geothermal energy is drawn from the heat inside the earth. Today, it supplies only a tiny fraction of the energy we consume each year, but its impact may grow as scientists master the technology that will make it possible to mine the heat of hot, dry rock hidden miles beneath the surface of the earth. In this issue of Science Screen Report, we'll be looking at this promising new source of energy for the future. Americans use a lot of energy, nearly half of the energy consumed worldwide. And the population is growing, so energy use may jump as much as 70% during the next 30 years. Most of our energy is generated from fossil fuels, coal, oil, and natural gas. But world reserves of oil and gas are limited and may run out halfway through the 21st century. Coal reserves may endure for another 200 years. Because fossil fuel supplies are dwindling, alternative sources of energy are being developed. The United States now obtains about 8% of its energy from nuclear power plants, and another 7% from renewable sources like hydroelectricity and biomass. Solar, wind, and geothermal sources account for less than 1% of energy consumption. A large-scale renewable source of energy must be found. And some scientists believe that a supply lasting many thousands of years may be stored right beneath our feet.
Can't see any distraction.
The source of this energy is the heat of the Earth itself, originating in its fiery consolidation of dust and gas 4 or 5 billion years ago. The sun flared into existence in nuclear explosions that rocked the Milky Way, flinging balls of molten metal into space and into each other, forming larger and denser masses. One of these balls of molten metal became the planet Earth. Now, billions of years later, the surface has cooled, but our vast oceans and continents are just a thin covering. The Earth's core is actually a rock-solid furnace, about 3,900 degrees Celsius, the equivalent of 7,000 degrees Fahrenheit. Surrounding it is the outer core, a seething molten mass of iron and sulfur. Above that is the mantle, a very hot amalgam of minerals, about 2,900 kilometers or 1,800 miles thick. Topping it all is the thin crust. This is generally over 5.5 kilometers deep under the ocean, which translates to 3½ miles. Beneath some mountain ranges, it can be as much as 50 miles below. The heat from the Earth's core continually flows outward. When temperatures and pressures become high enough, the molten magma rises, moving slowly up towards the Earth's crust, carrying the heat from below. Sometimes the hot magma reaches all the way to the surface, where we know it as lava. But most often, it remains below the crust, heating nearby rock and groundwater that has seeped deep into the Earth. This water sometimes gets as hot as 370 degrees Celsius, or about 700 degrees Fahrenheit. It travels back up through faults and cracks in the crust, reaching the Earth's surface as hot springs or geysers. Most of this hot water, however, stays deep underground, trapped in cracks and porous rock. This natural collection of superheated hot water is called a geothermal reservoir. Today, we drill into geothermal reservoirs to bring the hot water to the surface, where it can be used to spin turbine generators and produce electricity. Currently, geothermal water is used around the world. The largest power plant, the geysers in Northern California, generates more than 1,700 megawatts of power, 7% of the total electricity provided to this state. But as clean and reliable as geothermal power is, it has one major drawback. There aren't enough reservoirs. Though heat is plentiful beneath the surface, water isn't. This lack of water has provoked the search for another method of extracting geothermal heat. Hot, dry rocks are common granites that floated to the top of the molten planet billions of years ago. Deeply embedded in the Earth's crust, they are massive and virtually impermeable. Yet running throughout the rock are networks of small fractures that are the secret to turning these massive granites into the heating elements of future geothermal power plants. Scientists plan to pump cold water from the surface at high pressure down a hole almost 13 centimeters in diameter, or about 5 inches. From 2 to 5 kilometers underground, the cold water is forced sideways through tiny fractures in the granite. As it passes through the cracks, the water extracts enough heat from the rock to become steam. The steam gushes to the surface and drives a turbine. But before water can be forced through these impermeable underground granites and make this heat mining possible, the natural fractures in the rock have to be widened. This can be done by pumping water into the rock at pressures high enough to overcome the weight of the miles of earth on top of it. Here, a sample is subjected to the pressure of 3,000 atmospheres, causing microscopic cracks to give way, shearing the granite. By increasing the size of the fractures, even a millimeter, the permeability of the overall system can be increased by as much as 1 million times. Hot, dry rock technology has been tested in Fenton Hill, New Mexico. where it worked for 17 years, delivering superheated water to the surface from hot granite 2.5 miles underground. But as good as it wasn't good enough. Scientists believe that because the region is geologically unstable, when the water was pumped down to enlarge the existing cracks in the rock, the result was vertical fracturing. Here, water pumped down to be heated is forced deeper into the rock. This makes it expensive and difficult to recover. The process becomes inefficient and cannot produce energy at a low enough cost to make it worthwhile. Hot, dry granite exists all over the Earth, and its potential for use in geothermal applications is enormous if it can be found in geologically stable locations. In Australia, far from volcanic zones, these granites are firmly held in the grip of the continent. Here, scientists are convinced the rocks will fracture horizontally when water is pumped down to widen the cracks. When this happens, the water travels sideways through the fractures, making the extraction of heat much more efficient. Before choosing a site, scientists have to know whether the rock is hot enough and how deep it is. Fortunately, this information is readily available. By using the latest computer imagery, maps can be created from oil company records of temperatures almost 5 kilometers beneath the surface. That would be about 3 miles below. These show locations of hotspots, but not the size of the rock. To discover how large and how widespread these rocks are, geologists use detailed maps showing gravity highs and lows. With this information, they can zoom in on rock bodies as little as 1 mile across. Then, by crisscrossing the countryside, targeting emissions of radioactivity, the depth of the granite can be determined. Higher levels of radioactivity, tiny as they are, suggest shallow deposits of heat-bearing granite. These show up on the maps as white targets. Using the global positioning system, scientists are able to locate the inaccessible regions. Then they can travel to them and survey the area to determine the exact location of the granite hidden deep within the ground. Granite has less gravitational pull than heavier rocks, and in the presence of a massive granite body, the meter shows a gravity low.
That's 3040.
Pieces of the rock are collected for detailed analysis. Since most of the Earth's crust is kept hot by the radioactive decay of elements within granites, the combination of radioactive elements tells us how hot the granite might be. Back in the laboratory, each sample is reduced to rubble. The powdered rock is then melted to combine its elements and poured into wafer-thin discs. These are bombarded with X-rays to determine the combination of radioactive elements in the rock. Billions of years of radioactivity have created shallow deposits of hot rocks over much of the world. But scientists are looking for rocks that have been kept extra hot under a blanket of sediment. The dream of these scientists is a multi-level hot dry rock power station, producing clean electricity at minimal cost. Although it may be decades before this technology becomes reality, researchers believe it's worth the wait. Hot, dry rock will produce geothermal power that's clean, renewable, and sustainable for generations to come.
As a way to widen your horizons and stimulate your interest in pursuing scientific careers, Bridgeport RESCO, a Wheelabrator waste management company, sponsors this issue of Science Screen Report as a public service for the youth of this community.